Assalamu alaikum. In today's lecture, we are going to do the tutorial for the inductance calculation of a transmission line. And this is the first tutorial in which we are actually going to find the inductance of a composite conductor. This is actually a single phase transmission line that is composed of 3 wires of radius 0.2 centimeter for conductor X, and for the return circuit we have conductor Y, which has 2 wires of radius 0.5 centimeter. Now what we have to do, we have to actually find the inductance for both the conductors individually, first Lx Ly, and then we will find the total inductance. And this is the formula for the geometric mean distance, and this is the formula for the geometric mean radius, and the final formula for the inductance of phase is actually Lx is equal to 2 into 10 raised to minus 7 natural logarithm GMD over GMR. So starting from X side or X phase, first we have to find the GMD, right? So we have to find the GMD and GMR for finding the inductance of X side for the forward conductor, right? If I will write it generically, the GMD formula will be Mn. M is the actually equal to 3, because in X we have 3 conductors and N is equal to 2. So it will be 3 into 2, that will be equal to 6. Then we have to find the distance between the conductors of the two different phases. One is the forward conductor, the other one is the return conductor. So the distance between the forward and return conductor, right? So in X side conductor we have 3 different A, B, C conductors, and on Y side we have D and E conductor, right? So we will be finding the distances DAD, DAE, DBD, DBE, DCD, and DCE. So this will be the GMD for X side. And if you will look on the Y side, the GMD will remain same. So you are actually calculating the distance from DA, then DB, then DC, then EA, EB, EC. So there will be 6 terms in the GMD for the Y side as well, and this will be the same GMD for the Y side. So we have to calculate these distances. DAD is actually equal to 9 meter. DAE, AE is the hypotenuse of the right triangle between A, E and D. So for DAE we have 9 square plus 6 square, it is equal to under root 117. So DPT is equal to DAE. So it is actually also the right triangle hypotenuse. So this will be 117 under root as well. Similarly for DBE, the distance between B and E is actually 9 meter, and DC, DC and D, this is the right triangle, so it will be the hypotenuse value. DCD is equal to 9 square plus 12 square. So 9 square plus 12 square. So DCD is equal to 15. Similarly DCE is equal to under root 117. So these are the distance values that we have calculated. And here Mn, as I have already told you, that M is equal to 3. M is actually the number of conductors in X side, and N is the number of conductors in Y side. So this is equal to 6. So by putting the values of distances and Mn, you will get the formula n square into 117 3 by 2 into 15. So GMD value is 10.743 meter. Now for GMR, you have to calculate the distances between the conductors of the same phase. So we have 3 conductors on X side. So the GMR for the X side will be DAA, DAB, DAC, DBA, DBB, DBC, DCA, DCB and DCC. So we have 9 terms, and we have n square here. So we have 3 conductors in x side conductor, so it will be 3 square equal to 9. Now again we have to find the distances. Now one thing to look at in this formula, we have DAA, DBB and DCC. So this is actually the radius of 3 different conductors A, B and C, and from the question we know that they have the same radii, right? So it will be equal to r e raised to minus 1 by 4, and r value is 0.25 centimeter. So we will convert it into 10 raised to minus 2 meter into 0.7788. So this e raised to minus 1 by 4 is 0.7788. So the value of DAA, DBB and DCC, that will be equal to 0.25 into 10 raised to minus 2, 0.7788. So we will use the calculator to solve this term. Similarly, DAB is equal to DBC, DAB is equal to BC, is equal to DCB, CB and BA is equal to 6 meter, DAC is equal to DCA, AC is equal to CA equal to 12 meter. So the final equation for GMR will be 3 square into 0.25 into 0.7788 into 10 raised to minus 2 cube, because we have 3 conductors, so these are the 3 values, into 6 raised to 4 into 12 raised to 2. So after calculating this value, GMR will be equal to 0.481 meter. Now we have calculated the GMD value. GMD value for conductor X is 10.743 meter, and GMR value is actually equal to 0.481 meter. And the inductance formula is 2 into 10 raised to minus 7 ln 10 raised to 0.743 over 0.481. So GMD over GMR equal to 6.212 into 10 raised to minus 7 Henry per meter. Similarly, you can calculate the inductance for the Y side, and the formula remains the same, 10 raised to minus 7 ln GMD over GMR. GMD will be the same value for the as for the X conductor, but for GMR now you have to calculate again, because the number of conductors are reduced to 2 in Y side conductor, right? So now GMR will be equal to m square, and m here is equal to 2 because we have 2 conductors on Y side, and the distances DE, DDD, DED and DEE. DDE is equal to DED 6 meter, and the distances with the same subscript is actually the radius, which is 0.5 into 0.7788. This is the value of e raised to minus 1 by 4 into 10 raised to minus 2. So the GMR value will be 4 n square. This is n square. We have 2 conductors, so n is equal to 2. 6 square into 0.5 into 0.7788 into 10 raised to minus 2, and we have 2 conductors, so this is square, and the final value for GMR is 0.153. We will put this GMR value here, and the Ly, the inductance of the Y conductor, will be equal to 8.503 into 10 raised to minus 7 Henry per meter. So these are the individual inductances of X and Y conductor. Now if you have to find the inductance of the whole single phase transmission line, then you just have to add Lx and Ly, and this will be equal to 14.715 into 10 raised to minus 7 Henry per meter. So this is the way that you have to use in order to calculate the inductance of a composite conductor. Thank you.